episode of La Segunda Derivada, the podcast of the School of Engineering of UC Chile, begins a season with guests who will talk with Agustín Covarrubias about the current and future challenges of our society. A podcast that will address the role of science and technology in solving the most urgent problems, both locally and globally.
Sean todos y todas bienvenidas a un nuevo episodio de La Segunda Derivada, el podcast de la Escuela de Ingeniería. Este episodio haremos algo nuevo. En nuestro primer episodio en inglés entrevistaremos a John Browning, profesor asistente del Departamento de Ingeniería de Minería, además del Departamento de Ingeniería Estructural y Geotécnica de la Escuela de Ingeniería UC. Entre sus focos de investigación se encuentra la volcanología y el estudio del riesgo asociado a los desastres naturales, utilizando una combinación de trabajo en terreno, simulaciones numéricas y experimentación física para entender toda clase de fenómenos geotécnicos y geológicos. Okay, so John, to start, what would you say is the common thread underlying all your research?
So my research is predominantly related to a sphere of geology and volcanology called volcanotectonics, which it's quite a new discipline in geology, and it combines very specific aspects of geology, such as the study of tectonics, how the plates move and the earth deforms, and volcanology, which is essentially interested in the physics of how volcanoes erupt. It's those two things combined. And my research, really, the underlying thing that I'm trying to solve in my research is to understand why volcanoes form and when an eruption is going to happen. So I'm constantly sort of searching for this method, or this kind of holy grail of if we can forecast volcanic eruptions and how accurately we can forecast volcanic eruptions.
So that sounds really difficult. I imagine there's a lot of very complex interactions involved in study the eruptions of volcanoes, let alone predict them. So yeah. In that sense, what are the main ways you try to approach that, like forecasting an eruption? Like, what tools do you use to try to collect data on volcanoes?
Yeah, so the thing I'm interested in is the study of the mechanics of rocks. So rock mechanics is kind of a sub-discipline of like solid mechanics that I guess we all learn in engineering. So it's essentially about the way that the rocks in the crust deform and the way that the rocks in the crust break. So we know that in any volcano, magma, the stuff that forms an eruption, is stored at somewhere between like 10 kilometers or more and the Earth's surface, right? So the magma needs to get from that depth to the surface to form an eruption. And in doing that, it deforms all of the rock around, which we can monitor at the Earth's surface using GPS, global positioning systems or satellites. We can use INSAR, which again uses satellites to monitor how the Earth's surface deforms. We can use seismometers, which tell us about how the Earth is breaking, earthquakes, right? Small earthquakes. And so we use all of those techniques of the volcano to monitor and see when magma is moving or when it's breaking the rocks. And what I do is try and replicate some of those processes in the laboratory. So I have some laboratory equipment to break rocks and monitor things like the seismicity or the deformation of the rocks, and we try and scale that to what's happening at the volcano. But I completely agree with you. It's a really difficult thing because there are lots of parameters and aspects related to volcanoes that we still don't quite understand how they work. So that's why forecasting is challenging, but also really interesting.
So how close can you replicate the conditions in a volcano in a laboratory? Like the temperatures, the rock mechanics, the pressure. Is it really doable?
It's a great question. So what we often do is we have to use scaling techniques. So a volcano, might be several kilometers high and several tens of kilometers wide. So of course we can't do anything to that size in a laboratory. And what we often do is take small cores of rock, the material that makes up the volcano, and we take maybe a core of rock that's a few tens of millimeters. And then we subject that rock to the same pressures that the rock would experience inside the volcano. So a few tens or a few hundreds of megapascals, depending on the depth. So this is related to what depth the rock is. We can also recreate some of the temperatures as well. We have machines that can take the rocks up to around their melting temperature. So depending on the type of rock, maybe 1,000 degrees Celsius. And we can also recreate the kind of loading conditions that the rocks experience before they break. So again, a few hundred megapascals up to a gigapascal perhaps of force that's required to break the rock or create fractures inside the rock. So there are things that we can do like that, and then we can start to monitor, like I said, the seismicity or the way the rock's deforming. It's more challenging to deal with magma. Magma is a really difficult thing.
Yeah, I imagine the safety concerns are rather important there. So what you work on the field and in the lab, like what are the advantages there? Like what can you get in the field that you cannot get in the lab, and what can you get in the lab that you cannot get in the field?
So yeah, so part of my research is in the lab doing experimental work, and the other part of my research, in fact, I'd say 99% of my research is in the field, taking measurements. So the way that I do that is I'm really interested in studying old volcanoes, because in old volcanoes, and when I say old, I mean geologically old, so sometimes tens of millions of years old. And what that allows us to do is look inside the volcano. And this is something kind of cool and unique to geology. We can dissect very old volcanoes, so we can start to learn about the processes that happened inside that volcano when it was active. So for example, I'm really interested in studying the magmatic fractures. These are called dikes or sills. And they're long and thin lineaments of magma. And so they record the path that the magma took from deep toward the surface. So if we study these, we can understand something about how that magma rose through the crust to form the volcano. So I take measurements like the orientation, the size of these fractures. And we can try and recreate some of that information in the lab using analog models or using sort of rock mechanics techniques. But all of those lab measurements, they always need to be traced back, or they need to confirm the field data, the geological data that we take.
So when you study, by example, old volcanoes, where you have like a long history of activity, you obviously couldn't observe. We don't have historical records going millions of years in the past. What gaps appear in an understanding there? Like, what are things that haven't been explained yet, or perhaps there is a process, or there are new papers being published about?
So the cutting edge research that I'm mostly involved in relates to this fundamental question of how does magma get from depth to the surface? And this is probably related to the material properties, the different material properties that make up a volcano. We know that most volcanoes are made up, are what we call heterogeneous materials or composite materials, right? They're made up of different layers, and they're made up of different layers because the eruptions are different. They form different materials. So it's in essence, it's a material property problem. And we also know that fractures propagate more easily through some materials than they do through other materials. So in the field, we can take observations of the different layers that make up these old volcanoes, and we can take observations of when the magma passed through one layer when it didn't pass through another layer, when it changed its orientation in one layer. And so these are the kind of really interesting cutting edge things I think that we're all interested in, about how magma can actually get to the surface. When is it going to erupt? Why is it going to erupt in a certain point rather than another point? And in Chile, particularly, we often have this assumption that most volcanic eruptions occur along what we call fault lines, where earthquakes happen. We have many faults, active faults in Chile, and there seems to be a connection between the orientation, the direction of the faults, and the location of volcanoes. And it's still not really clear why. Why does the magma choose to take a fault when it could take another path? And so there's a lot of really interesting sort of mechanics problems related to this, but in essence, it's a material properties problem.
So it's really about improving our understanding about how the material properties, and like I imagine you have some micro problems, like how the materials work together in composite materials, but also very big geological problems, like how magma flows to the surface, how geological formations come into play there. So really you have a big scale you can cover here, like from the basic chemistry and mechanics of materials to like very big scale geological formations.
Yeah, and that's why geology is really interesting, because we have to look over the tens of kilometer scale, or if we're observing like other planets where there is volcanism as well, our only observations are really over the kind of kilometer or tens of kilometer scale. But we can also collect samples, and we can look at those samples under the microscope, and we can see like the micron scale. And actually, we know that for some processes, the micron scale, what's happening at the interface between crystals or grains that make up a rock, can be equally as important as what's happening over the like tens of kilometers scale for certain processes. So that's why geology is really interesting. We have to observe and we have to understand processes over all of these scales.
That's really impressive. I also imagine the disciplinary knowledge you have to study these kinds of things is very specific, right? I mean, I'm broad. I would believe like maybe I understand something about chemistry, but going from that to also understanding mechanics, dynamics, the complex process of geological formation, seismic activity. I mean, there's a bunch of things coming together in this field, and that has really impressed me.
Yeah, it's true. It's the basis of geology relies on an understanding of chemistry, an understanding of physics, and mechanics. So in many senses, it's a discipline very well placed in engineering, because we have to know about a lot of those different aspects of science, and of course mathematics, and there's a lot more computational skills now in geology that they're required. But we're talking about processes like at the very edge of the interface between crystals, like micron or millimeter size crystals. The way that those crystals form, the type of crystal, the size of crystals, that's fundamental chemistry, right? Then the way in which those crystals at the micron scale start interacting, start forming fractures, that's mechanics and physics. So very quickly there has to be an interplay between these different disciplines.
So I'm going to ask the tough question here. So you have all of this really amazing knowledge about how these volcanoes work, and maybe how they have formed through a very big scale of time. But on the micro scale, like on the short term, do you have the ability to actually predict eruptions? I mean, like we've seen the eruption of La Palma today in Spain. We've had the eruption of Kilauea again, which is a very active volcano, for what I understand. So is it possible to actually predict these eruptions to a reasonable time scale? Like, can we know that tomorrow a volcano is going to erupt, or maybe a few hours from now?
Sure. Yes, the answer is it depends which volcano, really. And it depends how well monitored. that volcano is. So in the case of La Palma and in Kilauea and the recent eruptions in Iceland, in the southwest of Iceland, those places are very well monitored. They have a very good seismic network, so we can listen to what the volcano is doing. They have very good teams of people who are monitoring the data and looking at how the ground is deforming. And in all of those cases, we knew for several days that magma was moving because there was a lot of seismicity. The seismicity could be traced to show the kind of the path or the form that the magma was taking. So in all of those cases, there was a good idea that it's likely that there's going to be an eruption. In earth sciences, we tend to prefer the word forecast rather than predict. They have slightly different meanings. And in those cases, we can make a reasonable forecast of the likelihood of an eruption. What it was more difficult to do in those cases, in La Palma and Iceland, is say where the eruption was going to happen exactly. There you can make some probability statements, and you could look at past eruptions to have some idea, but it was difficult to say precisely where. And that's because the physics are complicated, and there's probably a lot more that we could do in terms of the numerical models to address that. But other volcanic eruptions are somewhat more difficult, and it depends.
So I seem to be drawing some parallels here with climatology, right? Like climate science. I mean, first, the thing that you call forecast and not prediction, but also the way you have to predict. You're very limited in predicting with probabilities there, and you have very dynamical systems that behave very chaotically over time. So it seems there are at least some interesting parallels here. Well,
yeah, I think you're right. That's true. There are. We often, it has to be like probability statements. So how likely, and then how confident are we in that likelihood? And ultimately, it's the people who live at the volcano or who live in areas that are going to be affected by climate who are interested in those statements, right? Because we very quickly there starts to become an interplay between geology and all the scientific stuff that I'm really interested in, and society, the people, the communities who live on the volcano. And the problem becomes that if we start predicting eruptions and there isn't an eruption, then the next time, you know, people take the advice or the prediction with less seriousness. So there starts to very quickly become an interplay with how the science is communicated to the public, and I think that's another really interesting sphere of earth science and geography and humanities.
Yeah, you're right. I mean, a false positive here also have very, very important material costs. I mean, people have to move, escape, leave their belongings away. And it obviously isn't good it isn't a good experience for anyone evacuating. So you have to balance, obviously, the safety of the people, the probability that maybe you're having a false negative, and obviously the probability of causing a false alarm there. So I was actually reading a report from the United Nations Office for the Risk Disaster Reduction, the UNDRR, and I noticed they gave a very important fact. I mean, about a tenth of the global population lives near the risk zones of active volcanoes. So in that sense, how monitored are those risk zones in practice? I mean, you've given some examples of volcanoes that are actively monitored and forecasts can be made adequately to protect people, but are there good examples where that isn't happening? Like governments that maybe don't actively monitor or don't actively plan for disasters like that?
I'd be hard pressed to give examples of governments or countries that don't do it well, although there are many, I'm sure, but I'm not sure I'd want to go into detail with who doesn't do it so well.
Yeah, it's not to blame anyone, right? I only want to know whether there's a reasonable risk here we're talking about.
Well, there is a reasonable risk, and I think it is okay to blame governments if they don't do risk prevention activities, because it's their duty to prevent risk and to inform the population of the risks that people live in their countries. I can say that in Chile, it's done quite well in terms of the risk of volcanic eruptions, because most of the active volcanoes in Chile have hazard or risk maps prepared. Some of the volcanoes in Chile are quite well monitored, and that's largely because of the Sergnahuman and the volcano observatories, who do an incredible job of working hard to do that, probably without the resources they need. And so I think there can always be more help given to these people to do their job. I think that a good example of a volcano that perhaps we didn't understand as well as we should have was Chaiten, which erupted in 2008. And for various reasons, it was considered that it was probably like a dormant volcano, or a volcano that wasn't likely to erupt or had a high risk associated with it. And the consequences from that eruption were devastating for the people who lived nearby, because it destroyed large parts of Chaiten, the town. It coated Futaleufú and other areas in centimeters of ash. And so I think having a better understanding of all of the volcanoes in Chile would be of great help. And you think about Chile as a well-developed country, so we do quite well at it. There are definitely countries who do much worse.
But in hindsight, you look at Chaiten as by example, as an incident that could have been better prepared for? Could we have better alert systems, or better risk disaster scenarios, or better planning in that sense?
Yeah, I think so. I think in terms of Chaiten, which is a volcano that has historically produced very large, very explosive eruptions, I think making people aware of what that volcano could do over the timescales that it could do it was potentially a failing, or could have been done better. The challenge with the Chaiten eruption was that all of that whole episode occurred very, very quickly. We talked about La Palma and Iceland, where there was this buildup of seismicity for days and weeks even before. Actually, in La Palma, there was a paper published many, many months ago suggesting that something was happening, that the system was priming for an eruption. So people had a good idea about this. But at Chaiten, we didn't have that kind of foresight, and it seemed like the magma rose to the surface very, very rapidly within the space of about a day. So it was very difficult to prepare people. But even in those circumstances, there were evacuations, and I think most people got out. They did a good job of helping the people that they could. But I think we could know more about those systems.
I see. So I want to briefly change topics to a little bigger scale. Like we talked about how obviously volcanology really spans very big scales, but I mean, I was reading about, obviously preparing for this podcast, I wasn't going to come empty-handed.
Very good preparation, by the way. These questions are excellent.
I'm glad. So I was reading about the 1815 eruption of Mount Tambora, which caught my eye, because obviously, well, we think of volcanoes as these very big things that expel a very big amount of material, and they can have very big effects. we usually don't think those effects as having some effect on the planetary scale, right? Like if we think, I don't think, I was thinking about greenhouse gas emissions when I saw Titan myself. So Mount Tambora, as I think, caused even an entire year where the year without summer, which obviously caused a lot of other effects on human populations, not directly associated with the eruption itself. I mean, famines, all of the agricultural jobs basically stopped working because you don't have seasons. So how does that link between volcanic eruptions and climate science occur? Like, how do you go from A to B here?
I think the challenge here is comprehending just how powerful the Earth is. And that's incredibly difficult because the numbers are enormous. So an eruption like you described at Tambora had a clear impact on the climate. The amount of energy, the material that was released from that eruption that went into the atmosphere and caused a cooling for over about a year or more. There was another eruption in Krakatoa, which had similar effects. And these are big eruptions, but they're not the biggest eruptions that the Earth can produce. We have volcanoes that we know can produce eruptions of an order of magnitude greater than those kind of eruptions. Like you might have heard of the Yellowstone volcano in America, which is a caldera volcano that has historically produced enormous eruptions. We have volcanoes of similar size in Chile as well. Laguna del Maule is a caldera volcano which has the potential to produce very large eruptions. And these kind of eruptions, with the amount of material that they can displace, they can put into the atmosphere, fine grain material, they can potentially change the climate. We've seen that in the past, and it will happen again in the future. The challenge, of course, is we don't know exactly when, we don't know
where.
Yeah, or where.
What are the effects going to be? So yeah, a lot of unknowns there.
Yeah, well, we have some ideas of where. There are candidate volcanoes of which we have a reasonable idea that they're potentially cataclysmic or climate changing or extinction level eruptive events. And so, should I be worried about that existential risk? Because I already have a very big list of existential risks. We can't worry. There's too many things to worry about. I think we just have to try and understand the volcanoes and be interested in them as much as possible. But there's no use in worrying about these kind of things because at the moment there's nothing we could do.
Okay, so that's the same thing that I hear about, like people starting asteroid collisions. Like, yeah, so maybe there is a very reasonable risk to humanity, but we can't do much right now.
Right now, but maybe in the
right
future.
Now, that's important in the phrasing, right?
And so for asteroids, there's engineering and tests and all sorts of things going on to see if we can break asteroids to some extent. I think there's a new mission being launched this year that's going to try and test some of these ideas about whether you can nudge an asteroid. And in terms of volcanoes, perhaps in the future, we might think about ways to extract some of the energy from the volcano such that it has a reduced amount of energy that can be used for an eruption. We can think of a volcano just in
by
terms
example,
of
like putting a hole in the volcano to release some of the pressures and things like that.
Well, yeah. Well, at the moment, one of the things that's really important for Chile, particularly, and we do it in Iceland commonly, we do it in New Zealand, is extracting some of the energy from a volcano in the form of heat, the geothermal energy. And this is something that as a society, as a planet, we need to do more because it's it's a renewable resource, and it's a virtually endless resource as well. It's a fantastic way of getting energy and power. And we could do this in Chile, and I think we need to do it more. But if you just think of a volcano in terms of its energy budget, there's some energy that can go into heat that we can use to power, to heat our homes and to power electricity and various things. And there's some energy that can go into an eruption. So if we can switch some of that energy to some of the stuff we can use and take it away from what can go into an eruption, perhaps in the future, there's a way that we could prevent or minimize some future large, potentially cataclysmic eruptions for the future.
That's really impressive. I mean, the possibility of doing something like that to that scale of Earth engineering, Earth level engineering, I can think of many ideas there. So, so we are nearing half an hour. I want to talk for hours with you. I think we have a lot of topics to cover, but I have a bonus questions here. So while I was reading your research, because I had to do the homework, I noticed one paper that caught my eye, which was about marine pollution this year. So how did you get there?
So it's a long story that I can shorten a bit. So for most of the pandemic, I've been in Brazil with my family. My family are oceanographers who have for their life spent their life doing ocean conservation, and they set up various institutes in the state of Sao Paulo to do ocean conservation. And whilst I was in Brazil, there was an unfortunate case of a penguin that had been collected during one of the routine monitoring operations. And when the penguin was analyzed and dissected, it was found that the reason the penguin had died was because it had ingested a face protection mask, one of the COVID masks. And this, from what we understand, was the first example of any mortality, any marine animal mortality by this mechanism of ingesting like a face mask. And so we wanted to publish this paper because this was quite early on in the pandemic. So we realized there's going to be many, many months of this. And the problem is there are lots of people going to the beach with their masks, discarding their masks on the beach and then getting washed up. And it's more pollution, but a very specific form of pollution related to this pandemic. So it's related to my family, this unfortunate event, but trying to do something positive to try and get governments to think about how people are discarding their protective masks or gloves or whatever other protective clothing people are using during the pandemic.
So I love that. I mean, do you think that you would go out of your way to study something? Oh, I mean, you come from a family of scientists, I see. So I think so, I imagine some of that passion transfer to volcanology there. But yeah, I mean, it's a very important topic, and I find very cool that you could leverage some of your knowledge to help there too.
Sure, I think that's it. I think whatever we work on, we can always work on other stuff. And no one should be constrained.
That's the dilemma, right? We can always be working on a bunch of stuff.
we can work on what we're interested in. And as humans, we are constantly interested in other things and new things. So,
well, that's what I like about engineering. I mean, you can work pretty much on any topic you like. Not really any topic, but you can broaden your scope in a way that allows you to understand many scientific fields and the interplay between them. And I see that a lot of volcanology, obviously, because you really have a lot of interdisciplinary work, and there's no other way to understand this kind of phenomenon.
It's exactly right. Yeah, we have to know a broad range of things, and we have to work with other people. I think that's one of the key messages. We can't do it on ourselves. We have to work with other people. I'm not a chemist. I know I understand the things I need to about chemistry, but if I need to study a problem, specifically related to what's going on in the chemistry of my magma, I have to work with experts in chemistry. We have to do that all the time. And I think it's understanding this, that we don't have to know everything. We have to have an appreciation and an understanding, and then we have to have the confidence to ask for help.
So yet again, we've came to the same conclusion we've had once and once again on this podcast about interdisciplinary work and its importance to understand all kinds of phenomena we see, and the importance of, as you said, not only trying to know about everything, which is impossible, obviously, but also being able to recognize where we don't know something and being able to reach for help or to reach to someone who actually knows their stuff.
That's right.
Well, so thank you, John, for coming here. I didn't think, I was really impressed by your academic profile, obviously, but you're a really awesome person to talk about these things. My inner nerd is very glad that we had this conversation, and we'd love to see you again on this podcast, maybe for some other news of an eruption. I'll try to get an excuse there to get you here.
That sounds good.
So yeah, thank you for coming.
Well, thanks for having me, y muchas gracias por tener esta entrevista en inglés también.
Nos vemos en el próximo podcast, donde continuaremos abordando cómo desde la ingeniería podemos aportar al desarrollo de los países.
Las opiniones vertidas en este podcast son de exclusiva responsabilidad de quienes las emiten y no de este canal.